नमस्कार दोस्तों, मैं शिवानंद उपाध्याय आप सभी का स्वागत करता हूं हमारे YouTube चैनल केमिस्ट्री एकेडमी फॉर IIT JEE and NEET. This is the third day for JEE Mains revision, and today we are going to discuss about ideal gas, and tomorrow we are going to discuss about real gas. और मेरी आप सब लोगों से रिक्वेस्ट है कि if it is possible you share this video on your social media like Twitter and Facebook so that it can reach up to maximum number of needy students. Let us start our video. So let us start ideal gas. So the first thing I want to discuss is about experimentally derived law. So we know that there is Charles law, Boyle's law, Gay-Lussac's law. So we are starting with Boyle's law, which is very simple. So let us start Boyle's law. So about Boyle's law, we know that this is experimentally derived law. So according to Boyle's law, at constant temperature for fixed amount of an ideal gas, volume is directly proportional to 1 upon pressure, or we can say volume is inversely proportional to pressure, or PV is equal to constant. Now at the time of Boyle's law, there is no ideal gas equation. So at that time we are writing PV is equal to constant, but we know that PV is nRT. So no, we know the value of constant. The value of constant is mass of the gas upon molar mass of the gas into RT. So we can say that in this Boyle's law, the constant depends on 3 factors. One is the mass of the gas. It is directly proportional to the mass of the gas. It is inversely proportional to molar mass of the gas, and it is directly proportional to temperature. So there are many graphs regarding Boyle's law. We are going to discuss few which is important for our mains exam. So graphs related to Boyle's law. The first is PV is equal to constant. So on y-axis, if we take pressure, and on volume axis, x-axis, if we take volume, then we can write that y into x is constant, which is a rectangular hyperbola. On increasing volume, the value of pressure is going to decrease. And the second graph we can draw P versus 1 by V. So in place of pressure, we are saying this is on y-axis, 1 by V is on x-axis. So if we divide y by x is P upon 1 by V, that is PV is equal to constant. So y by x is a constant, and that constant we know that is nRT. So y is some constant into x. It is a line passing from origin. So pressure versus 1 upon volume is a straight line passing from origin, and the slope of that line is equal to this constant. This constant is nRT. So slope of the line is directly proportional to temperature. The third graph regarding this is PV versus V graph, or PV versus P graph. We know that P into V is constant. P into V we have taken on y-axis, so y is constant. Whatever the value of x, y is constant. It is a line parallel to x-axis. And the fourth graph, from here only we can write that if we take log on both sides, because we are taking log on both sides, so we can write that log P plus log V is equal to constant, or log P is equal to minus times of log V plus some constant. So if log P is y, log V is x, so it is a straight line whose slope is negative. So this graph is given in our NCERT, pressure versus volume graph. And for the same gas, this graph is drawn at 3 different temperature, and we have to find out what is the relation between T1, T2 and T3. So many questions are there in JEE Mains. They are asking into 2022 also. This type of question is there in JEE Mains, and this is very common. So let us discuss this question. So we know that PV is equal to nRT, right? If I take pressure constant, if I take a fixed value of P naught in place of in PV is equal to nRT, if I put that pressure is P naught, then I can write that volume is directly proportional to temperature for fixed amount of an ideal gas. V is directly proportional to temperature. And from here on x-axis, we can find out that for the top graph, since it is T1, I have kept the volume V1. For the middle graph T2, so volume V2. For the lower graph T3, so volume V3. So we know that V3 is less than V2 is less than V1. And volume is directly proportional to temperature. So from here I can say that T3 is less than T2 is less than T1. So in this way, we can find out what is the relation between T1, T2 and T3. So this is in NCERT. This graph is given in NCERT. Now this is the question asked in JEE Mains. In JEE Mains, they have asked this question. So let us discuss this question. They have drawn a graph of pressure versus 1 upon density. So we know that for an ideal gas, PV is equal to nRT or PM is equal to dRT. So from here, I can write that pressure upon density is equal to RT by M. So pressure is on y-axis and 1 upon density is on x-axis. So we can say that y into x here, since pressure is on y, so pressure 1 upon d is x, so y into x is constant. That's why this graph is rectangular hyperbola. So in this rectangular hyperbola, we have to find out the relation between T1, T2 and T3. So again, same way, if I fix the pressure, if I am saying that pressure is P naught in this equation, P is equal to P up into 1 by D is equal to RT by M. If pressure is P naught, now I am putting that this value is equal to P naught 1 by D is equal to RT by M. So I can say that 1 by D is directly proportional to temperature. So keeping the pressure P naught, now we can see on x-axis the density value is 1 upon D3, 1 upon D2 and 1 upon D1. This is 1 upon D values. So for first graph, since T1 we have taken, we are writing 1 upon D1. For second middle graph, T2, so 1 upon, for lower graph, T3, so 1 upon D3. So from here, we can say that as we are moving from left to right, 1 upon D values are increasing. And 1 upon D is directly proportional to temperature. So we can say that 1 upon D3 is less than 1 upon D2 is less than 1 upon D1. So same way we can say that T3 is less than T2 is less than T1. So this is the answer. This is the relation between T1, T2 and T3. Same type of question can be framed by drawing a graph of pressure versus density graph, right? So PM is equal to dRT. If I'm saying that pressure is Y and density is X, so from PM is equal to dRT, from here, let me write here that PM is equal to dRT. So if I am writing pressure is Y, RT by M is the constant and density is X. So it is a line passing from origin. That's why they have made 3 lines. And now we can compare on x-axis, there is density. So since for T1, this graph, we have used T1, so D1. For this middle graph, T2, so D2. And this lower graph, T3 to D3, right? So we know that on x-axis, D1 is less than D2 is less than D3. Same way we can say that T1 is less than T2 is less than T3, because here, we'll get the inverse relation, because when we are writing here, X and T are inversely proportional. Density and temperature are inversely proportional. That's why when we are writing that D1, D2 and D3, the temperature has inverse relation. We should write T3 is less than T2 is less than T1. Right? So these type of questions they are asking. Last year they have asked this question in JEE Mains. So very common question also given in NCERT. Let us move to second law, that is Charles law, and an easy way to remember, because Boyle's law everybody remember, right? Then after that there is a confusion between Charles law and Gay-Lussac's law. So in order to remember it in a more easy way, we can say that Charles has PC. PC was not there at the time of Charles, but we are just to remember it, we are saying that Charles has PC, means pressure has personal computer, pressure has constant in Charles law, just to remember it. So for fixed amount of an ideal gas at constant pressure, we can write that volume is directly proportional to temperature. And this temperature is absolute temperature, means temperature in Kelvin. From here, we can write that volume upon temperature is equal to constant. And now we know that volume upon temperature is nR by P. So this constant depends on 3 factors. Mass of the gas, it is directly proportional to mass of the gas. It is inversely proportional to molar mass of the gas. It is inversely proportional to pressure of the gas. So these are the graphs related to this Charles law. The first graph is volume versus temperature. We know that volume versus temperature we can write here by using this equation. PV is equal to nRT. So here we are saying that volume is equal to Y and temperature is equal to X. And this pressure is constant. So Y is equal to mx. It is a line passing from origin. But here on x-axis, the temperature is in Kelvin. When temperature is in degrees Celsius, then also they are asking the definition of Charles law when temperature in degrees Celsius. So the other way to ask about Charles law is the graph of volume versus temperature in degrees Celsius. So if we draw, we know that at 0 Kelvin means the temperature is minus 273 degrees Celsius. There is no gas because the gas will liquefy or solidify at 0 Kelvin. So that's why it is dotted. So when the gas is behaving like an ideal gas, we can write that V1 upon T1 is equal to V2 upon T2. So if the temperature T1 is 0 degrees Celsius, we can write in Kelvin 273.15 Kelvin, and T2 temperature in Kelvin is T degrees Celsius, then its value is equal to 273.15 plus T in Kelvin. And volume V1 at temperature T1 is V naught, because naught is for 0 degrees Celsius, and volume V2 is VT, means at T degrees Celsius. So if we simplify further, if we put the value of V1, V2, T1 and T2, we can write that V2 is equal to V1 T2 upon T1. And now if we put the value, VT is equal to V naught 1 plus T upon 273.15. So VT minus V naught is equal to V naught. If you simplify this, if you bring this, if you first remove this bracket, this is V naught and this is V naught into T. So if you simplify, VT minus V naught is equal to V naught into T upon 273.15. So another way to say about Charles' law, they will say that which of the following is correct about Charles' law. So they will say that when we are increasing the temperature from 0 degrees Celsius to T degrees Celsius at constant pressure. So when we are changing this temperature on increasing the temperature from 0 degrees Celsius to T degrees Celsius at constant pressure, the volume of gas increases by T upon 273.15 times of its initial volume. So whatever mathematical form here we are writing, this form is written in language that if we increase the temperature from 0 to T degrees Celsius, then the increase in volume is equal to T upon 273.15 times of the initial volume of the gas. So this is also a way to ask about Charles' law. It is not only that volume of a gas is directly proportional to temperature when pressure is constant, right? So this is also very important for us, right? So the third law, Gay-Lussac's law, again it is similar. Pressure in Boyle's law, temperature is constant. In Charles' law, pressure is constant. So in Gay-Lussac's law, volume is constant. So for a fixed amount of an ideal gas at constant volume, pressure is directly proportional to absolute temperature. And further, if we simplify, we can write that T1 upon T1 is equal to P2 upon T2. We can write in this form. P1 upon T1 is equal to P2 upon T2. And again, if we want to write Gay-Lussac's law in different form, like here I am writing that temperature is T1 and temperature is T2. T1 I have taken T1 degrees Celsius, T2 I have taken T2 degrees Celsius. So pressure at T1 Kelvin is equal to P1. So P1 is denoted by PT1 and P2 is denoted by PT2. So if I calculate what is the value of P2, P2 is equal to T2 upon T1 into P1. If we put the value, we are getting P at T2 degrees Celsius and P at T1 degrees Celsius multiplied by T2 upon T1. So if I put the value of T2, T2 is 273.15 plus T2 degrees Celsius. And here in the numerator, I am adding T1 and subtracting T1. So this will cancel out. So basically, I am writing T2 divided by T1. So if I simplify here, 273.15 plus T1 in the numerator and denominator is equal to 1. So if I simplify, I can write this value is equal to PT2 minus PT1 is equal to PT1 multiplied by T2 minus T1 upon 273.15 plus T1. So I want to say that sometimes they will not say that Gay-Lussac's law in a simple way. In a simple way, we are saying that when volume is constant, pressure is directly proportional to absolute temperature. But they can also say that when we increase the temperature of a gas from T1 degree Celsius to T2 degrees Celsius, then the increase in pressure of the gas is T2 minus T1 upon 273 plus T1 times of initial pressure at constant volume. So this is also a way to say Gay-Lussac's law. Another important point is that This Gay-Lussac's law can be derived with the help of Boyle's law and Charles' law. With the help of Boyle's law and Charles' law, we can derive Gay-Lussac's law. The fourth law is Avogadro law. Everyone know about Avogadro number, Avogadro law, not number. Avogadro law, according to Avogadro law, under same condition of temperature and pressure, volume of a gas is directly proportional to number of moles of the gas, or we can say equal volume of two different gases contains equal number of molecules. So this Avogadro law is derived from Dalton's law. So it is a conclusion of Dalton's atomic theory and Gay-Lussac's law of combining volume. So what is Gay-Lussac's law of combining volume? When we are writing chemical reaction and in idiometry we are solving question that under if this reaction is taking place at the same pressure and temperature condition, then in terms of moles we are writing that 2 moles of hydrogen gas will react with 1 mole of oxygen gas to form 2 moles of water vapor. So if pressure and temperature is constant, volume is directly proportional to number of moles. So in place of number of moles, we can also write in terms of volume that 100 ml of hydrogen gas is reacting with 50 ml to form 100 ml of water vapor. So this we are using in idiometry, very common. So that is known as Gay-Lussac's law of combining volume. When gases combine or produce in a chemical reaction, they do so in a simple ratio by volume provided all gases are at same temperature and pressure. So Avogadro law is basically a conclusion of Dalton's atomic theory and Gay-Lussac's law of combining volume. And if we combine Boyle's law, if we combine Charles' law, and if we combine Avogadro law, then combining all these three, we can derive ideal gas equation. So we can say that a gas follows Boyle's law, Charles' law, and Avogadro law is strictly called an ideal gas. So an ideal gas will follow Boyle's law, Charles' law, and Avogadro law. And of course, Gay-Lussac's law is derived from Boyle's law and Charles' law, so it will also follow Gay-Lussac's law. Now we have already discussed that according to old STP condition, the standard pressure is 1 atm and temperature is 273.15 Kelvin. So 1 mole of an ideal gas according to old STP has a volume of 22.4 liter. Same way, under new STP condition, at new STP condition, we can say that pressure is equal to 1 bar and temperature is equal to 273.15 Kelvin. So if we calculate the volume of 1 mole of gas, which is known as molar volume, which is equal to 22.7. And now this is also important, standard ambient temperature and pressure. Standard pressure means pressure is 1 bar. Ambient temperature means temperature is room temperature, that is 298.15 Kelvin. So if we calculate volume occupied by 1 mole of gas, that is equal to 24.789. So these things are given in NCERT. So you should especially remember this standard ambient temperature and pressure. So volume of 1 mole of gas is equal to 24.789 liter. Now, whenever we are going to solve questions of ideal gas, like there are many questions based on container. So for an ideal gas, there is a key that PV is equal to nRT. R is universal gas constant. It means that PV upon NT is universal gas constant. So you can apply this formula everywhere. So there are many problems of gaseous state based on container which will follow this concept to solve it. It may be possible that during a process, pressure is changing, volume is changing, number of moles is changing, temperature is constant. Then we can write that P1 V1 upon N1 is equal to P2 V2 upon N2. Or it may possible that all is changing. Then also we can write that P1 V1 N1 T1 is equal to P2 V2 N2 T2. So there are many questions based on ideal gas. And for all those processes in which ideal gas is participating, then we can apply that universal gas constant is PV upon NT. means P1 V1 N1 T1 is equal to P2 V2 N2 T2. Like this particular question is also solved on the same concept. So this is a very common question in which they will say that there are two ideal gases. One is in container A and the other ideal gas is in container B. Gas A is at pressure P1, volume V1, temperature T1, number of moles N1. Gas B is at pressure P2, volume V2, number of moles N2 and temperature T2. If we remove the stopcock and will not change the temperature of these two containers, they will remain at T1 and T2. Then find out what is the final pressure of this system. So again, in this whole process, we can apply this formula, or in this whole process, we can say that the number of moles of gas is not changing. They are not reacting, right? So they are not changing. So we can say that number of moles of initial and final will be same. So initial number of moles we can calculate by using ideal gas equation. This N1 can be written as P1 V1 R T1. R I am not writing because it will cancel out. So P1 V1 upon T1. Number of moles in this container is P2 V2 R T2. And number of moles finally after removing the stopcock is N1 dash. The value of N1 dash, the number of moles in this container is equal to P final, because it is open. So pressure on left and right both will be same. So P final into volume V1 upon RT1. Temperature is not changing. It is given in the question, right? And again here P final V2 upon RT2. So R on left and right will cancel out. And from here, if we know T1, T2, V1, V2, and if we know what is P1 and P2, we can calculate what is the final pressure. So many questions based on that. There is a question, I think it is in Bansal sheet, that if we are compressing a gas and there are many pistons, and these pistons will open at a particular pressure, when pressure will when the pressure exceeds a particular value, then a particular piston number 1, piston number 2, piston number 3 will open. So in those questions also, when we are applying this formula, that when the number of moles, suppose a piston will open, then the number of moles will be variable. Then we can write that P1 V1 upon T1 is equal to P2 V2 upon T2. Right, so we are using those things. When number of moles is constant, then you can write P1 V1 upon T1. When it is variable, you can write P1 V1 N1 T1 is equal to P2 V2 N2 T2. So I think in that question, temperature is not changing, temperature is constant, pressure is changing. So P1 V1 N1 is equal to P2 V2 N2. So a lot of question based on this concept, and this is the key to solve them. This is always valid. Keep in mind, in that way you can solve many problems. Let us move further. So till now we are discussing about experimentally derived law, and this is also one of the law, Dalton's law of partial pressure. So according to Dalton's law of partial pressure, we are writing Dalton's law in two forms. One is partial pressure of the gas. Partial pressure of the gas is equal to mole fraction of that gas into total pressure. And the second way is sum of partial pressure of all the gases in the container is equal to total pressure. So these are the two forms of Dalton's law of partial pressure. So if you read books, you will find that Dalton's law is strictly valid only for mixture of perfect gases, but it can be treated as valid under most conditions we encounter. Why I am discussing that? If they are saying that ki Dalton's law strictly kiske liye valid hai, it is strictly valid for ideal gas. We are going to prove, because suppose if in this gaseous mixture, non-reacting gaseous mixture, there are gases A, B and C. So partial pressure of gas A is equal to number of moles of gas A RT by V. Partial pressure of gas B is equal to number of moles of B RT by V. Partial pressure of C is equal to number of moles of C RT by V. So first thing is that when we are calculating partial pressure, because this A gas is in the mixture of ABC, but what pressure it is applying when it is only present in this container at the same temperature, that is the partial pressure of A. When only B is there in this container at the same temperature, whatever the pressure it is exerting on this wall is partial pressure of B. So partial pressure of a gas depends on only three factors: number of moles of that gas, temperature, and volume of that container. So partial pressure of gas A depends on number of moles of gas A, temperature of the container, volume of the container. It is independent of number of moles of gas B. It is independent of number of moles of gas C. So sometimes they will ask a question that this is a container and keeping the volume constant, if we add a inert gas, what will happen to the partial pressure of A? There is nothing happen to the partial pressure of A on adding inert gas at constant volume, because temperature will not change, volume will not change, moles will not change, so partial pressure of A is not going to change. Definitely the composition, the mole fraction will change, the total pressure will change, but there is nothing going to happen on partial pressure of gas A or partial pressure of gas B or partial pressure of gas C. So the point is, partial pressure of a gas depends on number of moles of that gas only, and temperature and volume of the container. If all these three are not changing, partial pressure is not going to change. It may possible that total pressure will change, composition will change, but partial pressure only depends on three things. So we have derived this way. One way is saying that partial pressure of gas is mole fraction of gas in P total. Partial pressure of gas B is mole fraction of gas B into P total. So what I want to say that when we are saying PA plus PB plus PC is equal to P total, we can only derive when we are using PV is equal to nRT. This is ideal gas equation. Van der Waals real gas equation, from there if we want to derive, will not get this value. So strictly speaking, we are using, or we are saying that Dalton's law of partial pressure is valid for ideal gas, but we are also using for real gases also in most of the cases, because the first thing in NCERT they have given, like if we are collecting a gas over water. So now water is volatile substance. So water is there in gaseous state and a gas, suppose nitrogen gas is here. So now nitrogen gas and water vapor is there. So if we, by putting some manometer, we can find out what is the total pressure of this gaseous mixture. So P total is equal to pressure of this dry nitrogen gas plus pressure due to water vapor. And since there is an equilibrium, we can say that at equilibrium, vapor pressure of water is known as aqueous tension. So we can write that partial pressure of dry gas is equal to total pressure minus aqueous tension. So why I'm discussing, because in Dumas method is used to determine the amount of nitrogen in organic compound. In Dumas method, we collect nitrogen gas over water. So we are using this concept. And we know that water is present in liquid state. So definitely it is not an ideal gas, because ideal gas cannot be liquefied. So that's why this statement is important. Strictly, it should be valid for perfect gas, but it can be treated. It is valid for most of the gases we encounter. Why I'm saying again, when we study liquid solution and we are saying that A and B are two liquids and on mixing they are forming an ideal solution, then we'll say that total vapor pressure of the solution is equal to vapor pressure of liquid A plus vapor pressure of liquid B. Again, they are liquid and gas both. So they are not ideal gas, but we are using that Dalton's law, that total pressure is equal to sum of partial pressure of the gaseous substances. Let us come to the application of this Dalton's law, because there are questions, many questions, most of the question they are asking based on Dalton's law only. So first point I have already discussed, that partial pressure of an ideal gas only depends on its mole, volume and temperature of container. It is independent of moles of other gases. I have already discussed. The second point is, pressure can be different on two sides of a rigid wall, but pressure will be same on left hand side and right hand side of a movable piston. This I have to discuss. There is a confusion. Suppose when we are saying that in a container, this is a movable piston, and on two sides of this piston there are two different gases. Suppose we are saying that initially this gas is at pressure 10 atm and this is at 5 atm, and there is a mechanical stopper. If we remove the mechanical stopper, this piston will move. So this piston is movable, and when the pressure on both sides are different, then it will move until the pressure on left hand side is equal to pressure on right hand side. But that is not valid for a fixed wall. Like you are putting a cylinder, cooking cylinder is there, right? And inside the cylinder the pressure is very high, outside the cylinder the pressure is 1 atm. So when we are talking about a fixed wall, on two sides of a fixed wall, the pressure can be different. So based on that, this problem is there, this example is there. Let us discuss this example. They are saying that, let me read the question. This is the question. So here there is diagram, and on the left hand side, the volume of the left part of this container is 10 liter. On the right hand side, the volume is 8 liter. If we simultaneously introduce 4 mole of hydrogen gas on the left hand side container, so on the left hand side we are putting hydrogen gas and the number of moles is 4, and 4 moles of nitrogen gas, so nitrogen gas is there on right hand side and number of moles is 4 on the right hand side. Then find the number of moles of hydrogen gas in the first and second part of the container. So they are saying this is the first part of the container and this is the second part of the container. And they are saying that this container has fixed semi-permeable membrane which can allow passage of only hydrogen gas, because hydrogen gas is smaller in size, so it can pass through this semi-permeable membrane. But the size of nitrogen is big, which this permeable membrane is not allowing to move nitrogen, but it can allow movement of hydrogen gas. So whenever a gas can move from its high pressure to low pressure, right, it will move till its pressure on both sides will be equal. So again here we are saying that hydrogen gas can move from left hand side to right hand side. It will move when the pressure of hydrogen gas on the left hand side and right hand side will be equal. So they are asking that find out the number of moles of hydrogen gas in first and second containers. So under the equilibrium condition, we can say that the partial pressure of hydrogen gas on the left hand side and the partial pressure of hydrogen gas on the right hand side, on both sides of the container, the partial pressure of hydrogen should be same. So partial pressure of hydrogen gas is equal to number of moles of hydrogen gas, volume of container in which it is present, into RT. So here they are not mentioning anything about the temperature. Not mentioned means temperature is not important, means temperature is not changing. So we are assuming that temperature is same throughout and it is not changing during the process. Temperature is constant. R is universal gas constant. So we can say that partial pressure of hydrogen gas is directly proportional to concentration of hydrogen gas. And finally, under equilibrium condition, if the pressure of left hand side of hydrogen and pressure on right hand side of hydrogen is equal, it means that the number of moles of hydrogen gas upon volume of hydrogen gas on left hand side is equal to number of moles of hydrogen gas upon volume of hydrogen gas on right hand side. So some molecules of moles of hydrogen is moving from left to right. Assume X. So the left amount is 4 minus X. So we can say that 4 minus X upon 10 liter is equal to X upon 8 liter. Partial pressure of hydrogen gas and left and right is equal, means concentration of hydrogen gas on left and right is equal. And from there we get this equation. On solving this equation, we are getting that if we write here, if we simplify, this is 5 and this will be 4, and cross multiplying, we are getting that the value of X is equal to 16 by 9. So we can calculate 4 minus X, that is equal to 20 by 9. So these type of, there are many questions based on this, right? Here you can say that the pressure on the right, total pressure I'm talking, total pressure on the right is greater than left, because here left and right pressure of hydrogen gas are equal, and here nitrogen gas is also there. Its pressure will be more, so total pressure is pressure of hydrogen plus nitrogen. So since it is a fixed wall, pressure can be different on left and right, and if a gas can move, it will move till the partial pressure of the gas on both sides will be equal. If temperature is constant, pressure is directly proportional to concentration, and concentration is number of moles upon volume. So these are very common question based on Dalton's law of partial pressure. But in JEE mains, they are asking very simple question. They can say that in a container, right? Okay, let us discuss this point also. This is also very common. Okay, here it is not mentioned. So let me discuss here. They can say that in a container, some nitrogen gas is collected over water. So this is temperature T and nitrogen gas is there, and this is water. There is an equilibrium water between water in liquid state and vapor state. So we'll say that if there is an equilibrium, this vapor pressure of water is known as aqueous tension. So suppose this is the condition initial. So I can say that this P total is equal to pressure of dry gas, that is nitrogen gas, plus aqueous tension. Now they are saying that if we double the volume of this container, keeping the temperature constant, if we double the volume, double the volume of this part, gaseous part, right, where the gas is there, if we double it, what will happen? So on doubling the volume, there is no change in aqueous tension will remain same. Definitely the total pressure is going to change. So now since the volume of this nitrogen is behaving like an ideal gas, so if we double the volume, pressure will become half. So I can write that now the P total dash is equal to whatever the pressure of dry gas was there initially, it will become half, but there is no change in aqueous tension. Aqueous tension of a gas, of a liquid or a substance, volatile substance, only depends on temperature. So on doubling the volume, aqueous tension is not going to change, but for an ideal gas, on doubling the volume, keeping the temperature change, the pressure will become half. So this is very common in exams. Mains, they are asking these type of concept. Okay, so the next point is Graham's law of effusion and Graham's law of diffusion. The first thing is that if you go through your NCERT, they are writing effusion oblique diffusion, right? But there is a difference between effusion and diffusion. When we are talking about effusion, it is leakage of a gas in vacuum. So if a gas is there and it is passing through a tiny hole into vacuum, then it is known as effusion, and effusion is always followed by diffusion. When we are talking about diffusion is intermixing of two gases, and basically practically if diffusion is more common in our life, like if we are making a gas and the cylinder is leaking, right? So in the cylinder they will put some gas which has a particular smell. Mercaptan gas is there which has a particular smell, and it will tell that okay, there is a gas leakage. So when that gas is moving, already there is air in the room, right? So when the gas particle is coming out of that cylinder, it is colliding with the particles of nitrogen and oxygen present in the container. This is mixing of two gases. So diffusion is related to mixing of gases, while effusion, we are saying that there is a leakage in vacuum, right? And effusion is always followed by diffusion. So when we are discussing about rate of effusion, suppose in this container there is a ideal gas and the area of the hole is equal to A, temperature of this container is equal to T, there are n moles of the gas and volume of the container is V. And we can say that this hole is present along X, matlab, we can draw axis and we can say that this is X direction, right? So this hole is perpendicular to X direction, we can say. So we can write that rate of effusion is directly proportional to area of the hole. More the area, more will be the rate of effusion. It is obvious, more larger size, more molecules can go, because in this container the gas particles are moving in random motion and they are colliding with the wall of container. So where there is no wall, at that place the gas particle will go away. The rate of effusion is directly proportional to number of particles per unit volume. Definitely if the particles will be more at that at a particular point, the chances of collision will be more. So rate of effusion is directly proportional to number of particles per unit volume, means it is directly proportional to pressure of the gas, because P is equal to N by V into RT, temperature is constant. So P is directly proportional to N by V. So it depends on pressure of the gas. More pressure means more collision, gas can go more easily outside. And the third is rate of effusion is directly proportional to average speed of gas particle in this direction, which is I have taken X direction. So these are the three factors on which rate of effusion will depend. And if we write what is the average speed of gas particle in a particular direction, when we are using a formula of average speed, it is in all direction. We are using U average is equal to under root 8 upon pi RT by M. So here it is in particular direction. So all things will be same, means temperature, molar mass will be same, only the constant will change, right? So here they have written in terms of U average in a particular direction is RT upon 2 pi M. So if we put all together, we can say that rate of effusion is equal to some proportionality constant K, whose values was found to be 1 experimentally, into area of the hole into average speed in x direction into number of particles per unit volume. So if we further simplify that, we can say that rate of effusion is directly proportional to area of the hole, average speed in x direction, that is equal to RT 2 pi capital M, and this N by V. So N by V, we can find out number of particles per unit volume by using PV is equal to nRT. I can write that PV is equal to nRT. I have to write number of particles per unit volume, that is equal to P upon RT. It should be P upon RT, P upon RT. So this R is a constant. So we can say that rate of effusion depends on 4 factors. One is area of the hole. The other is pressure of the gas inside the container. And if we simplify, molar mass is coming in denominator under root M. And if you simplify this temperature under root is coming here. So rate of effusion depends on pressure, area, under root of molar mass and temperature. Now most of the student has remembered that on increasing temperature, rate of effusion will increase, because they will think that on increasing temperature, speed will increase, so particles will go more fast, right? So we have to define that under what, like if I am saying that if the process is isobaric, if pressure is constant, then I can say, okay, rate of effusion is inversely proportional to under root T. So on increasing temperature, then effusion will decrease. Because if you are increasing temperature, many things are happening. Collisions are also increasing. So due to increase in collision, since the particles, that hole size is very small, if the collision will increase near the hole, effusion is going to decrease. So it not only depends on hole and speed, it also depends on the number of collision. On changing the temperature, collisions are also changing because of that. So this is a common error, like this, whatever the student remember and relate is valid when volume is constant. When volume is constant, then you can say that pressure is directly proportional to temperature. So in place of this pressure, you can write temperature, and then you can say rate of effusion is directly proportional to under root of temperature, right? So this is very important. It is a common error done by a student, right? And you should remember that rate of effusion is directly proportional to PA upon under root T and M. And then you can relate, because they can say isochoric process, adiabatic process. They can ask very good question by using this concept. So you know that for adiabatic reversible process, PV to the power gamma constant, right? Or temperature pressure relation, you can write and find out how the rate of effusion is going to vary, right? So this is the 4 factors on which rate of effusion depends. Now the most common question asked about rate of effusion is, in the same container, 2 gases there, A and B gases are there. And this concept is asked because in order to separate uranium 235 and uranium 238, because in nuclear reactor we need uranium 235, and in nature uranium 235 is very small, so we convert uranium into uranium hexafluoride. So there are 2 uranium hexafluoride, uranium with heavy uranium 238 and uranium with lighter uranium 235. So what we are doing that, by using the molar mass of 2 gas, one is lighter and one is heavier, and applying the concept of effusion, we are separating uranium 235 from uranium 238. So that's why this question is there, that in a container, if 2 gases are there, A and B, one of them is lighter and the other is heavier. Since they are present in the same container, so volume of that container will be same, temperature of that container will be same, area of hole will be same. So the rate of effusion will depend on partial pressure of gas, because we are saying rate of diffusion or effusion depends on 4 factors, PA upon under root M and T. Since same container, so temperature will be same and area of hole will be same. So it depends on partial pressure gas and under root molar mass of the gas. So here we are writing that rate of effusion of gas A upon rate of effusion of gas B is equal to partial pressure of gas A upon partial pressure of gas B, under root molar mass of gas B upon molar mass of gas A. And partial pressure of gas A is number of moles of gas A RT by V, number of moles of gas B RT by V. RT by V will cancel out because they are present in the same container, temperature and volume will be same. So we can also write that rate of diffusion of gas A upon rate of diffusion of gas B is equal to number of moles of that gas, number of moles of B gas, and this is molar mass. This relation can further be simplified. There are so many ways to represent the left hand side. We can represent rate of diffusion by decrease in pressure per unit time, decrease in number of moles per unit time. So here we have written decrease in number of moles. Since it is simultaneous, so time for both will be same, so it will cancel out. So we can write that number of moles of gas A effused upon number of moles of gas B effused is equal to this. Again, number of moles is mass of A upon molar mass of A, change in mass of A upon molar mass of A. So molar mass of A on the left hand side and right hand side will cancel out. We can write in terms of mass of the gas also. So mass of the gas A effused upon mass of the gas B effused is equal to initial mass of A, initial mass of B under root molar mass of B upon molar mass of A. So good question of that is related to JEE Advanced, but the simple question is based on this basic formula. Most of the question asked in mains is based on this basic formula. So what is important? You remember that it depends on 4 factors. This formula is important, and how we are going to apply. If two gases are present in the same, then it depends on partial pressure and molar under root molar mass of the gas. Now the second question is about diffusion. When we are talking about diffusion, we are talking about intermixing of gases. Like they will say that there is a tube, on one side of the tube in a cotton we put HCl gas or HCl, we put a cotton, we dipped a cotton in HCl liquid, and because HCl is volatile, and then we put on this side of the tube and this side of the tube. So in the tube there is hydrogen, there is oxygen and nitrogen, air is already there. So when this ammonia gas is going here, it is colliding with the nitrogen and oxygen present here. When the HCl gas is going here, it is colliding with the gases present in this container, air present in the container. So diffusion is a more complicated way, thing in order to theoretically discuss it. But good thing is that under the same condition of pressure and temperature, we have found experimentally that rate of diffusion of gases is also inversely proportional to molar mass. So that's why we are using this, that rate of diffusion of lighter gas, ammonia gas, upon rate of diffusion of heavier gas is inversely proportional to under root of molar mass. And rate of diffusion means distance traveled per unit time here. So we can say that the lighter gas is ammonia, it will travel fast. So the distance traveled by it is equal to x, and same time, in the same time, the distance traveled by HCl gas is equal to L minus x. So here I can put distance upon time, time is common, it will cancel out. So x upon L minus x is equal to under root molar mass of HCl upon molar mass of ammonia. So on putting the value, we know that molar mass of HCl is equal to 36.5 and molar mass of ammonia is 17. If we simplify that, we'll get the value of x, where there is a formation of white fumes of NH4Cl. So these type of questions are there. In case of diffusion, they will make another question that one side in a classroom, a teacher will release a weeping gas, tearing gas. On the back benches, the student will release a laughing gas, right? Tell me the number of bench where the student will first laugh and then it will weep, and simultaneously it is laughing and weeping. So those things are there in JEE Advanced, but we don't want to discuss here. These two things are enough. So this is related to effusion and this is related to diffusion. Kinetic theory of ideal gas. This is also important in physics, right? So there are certain points. I have written all the points in short. So let us go through the points one by one. The first point is volume of ideal gas is negligible with respect to volume of container. So in case of ideal gas, volume of container is free volume. Between two collisions, gas particle is moving in a straight line. This is a very important point for exam. When you are writing kinetic energy of an ideal gas, you are writing that total kinetic energy you are writing. That is equal to 3 by 2 nRT. This is only translational kinetic energy. It is not rotational and vibrational kinetic energy. It is only translational kinetic energy. So for point mass, we only consider translational kinetic energy. So in ideal gas, we assume that gas particles are point mass. So we can only talk about translational kinetic energy. So between two collisions, they are moving in a straight line. So this point is very important for exam. So many times they are asking between two collisions, what is the motion? Motion is a straight line. Third point, collision is perfectly elastic. Yes. When they are colliding, one gas particle is colliding with each other or with the wall of container, the collision is perfectly elastic. And because of perfectly elastic collision, there is conservation of linear momentum and conservation of energy. Fourth point, gravity does not act on gas particle. If it is acting, then the pressure down the container is more and up the container will be less. So gravity is not acting on gas particle, but Newton's second law is valid. How Newton's second law is valid? We are saying that rate of change of momentum is force. So we are saying that when gas particle is going and colliding with wall, it is applying force on the wall. Force upon area is pressure. So Newton's second law is valid, but gravitational law is not valid for ideal gas particles. Fifth point, pressure is due to collision of gas particle with the wall of container. Yes, they will ask that pressure is because of what? Because of gas-gas collision? No, it is because of gas particle is colliding with wall. It is applying force on wall. Force upon area is pressure. So pressure is due to collision of gas particle with the wall of container. And due to random motion of gas particle, if there is random motion, then the probability of colliding the gas particle at each and every corner in the container will be same, and because of that pressure will be same. And the last point is average kinetic energy is directly proportional to absolute temperature. So with the help of these, we will able to prove that PV is equal to 1 by 3 small m capital N U square mean. This is also important. PV is equal to nRT, and this is other form of ideal gas equation. P is pressure of gas, V is volume of container, M is gas of one particle, and same type of gas is there. This is mass of one gas particle. N is the total number of particles in the container, and U square mean means it is average of square speed. So this U square mean is u1 square plus u2 square plus dot 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 un square upon n. This is average of square of speeds of all the gas particle. So from here, if you simplify, if you put 3 on this side, I can write 3 times of PV is equal to m into n. Okay, so m into n. From here you can say that if I bring this n on the left hand side, I can write that n into u square mean is equal to u1 square plus u2 square plus dot dot dot. So here in this equation 3 times of PV, and in place of n into u square, I have put this value from here, m n into u square की value यहाँ पे रख दी. So we can write 3 PV is equal to m into u1 square plus u2 square. If we divide by 2 on both sides, then this is equal to half into m into u1 square, half into m into u2 square. So this is total kinetic energy. So total kinetic energy is equal to 3 by 2 times of PV, and PV is equal to nRT. So from there we have derived that total kinetic energy is equal to 3 by 2 nRT. And total kinetic energy is extensive variable. It depends on the number of moles of the gas. While average kinetic energy, this is important point, they will say in many questions that in a container there are 10 moles of oxygen gas, in another container there are 20 moles of neon gas, and both are present at same temperature. What is the ratio of average kinetic energy? Average kinetic energy is intensive variable. It does not depend on number of moles, it only depends on temperature. If temperature of both the containers will be same, average kinetic energy will be same. So be careful about that. And this total kinetic energy is not all kinetic energy, it is only translational kinetic energy. So this is about average kinetic energy and translational kinetic energy. Average kinetic energy is intensive variable. It only depends on temperature, while total kinetic energy is extensive variable. It also depends on number of moles. And let us discuss Maxwell distribution of speed. This equation is not in your syllabus, right? Not in JEE Mains and Advanced, but this equation is very useful to understand the graph given in NCERT. These graphs are given in NCERT, and in order to understand these graphs, we need this equation. So let me explain this equation. This dn, small dn, is the number of particles in a small, like if we divide the speed, because in a container there are Avogadro number of particles, which is very large in number. This ideal gas equation or all the equations in ideal gas will be valid when the number of gas particle is very large. So of the order of Avogadro number. So in large gas particle, Avogadro number of particles, different particles have different speed. So we have divided the speed of these gas particle in small range. So we are saying that here, if this is u, then this speed is u plus du. So we are discussing about this speed range du. In this speed range, there are some particles, those particles are dn. So in different speed range, this number of particles are going to change. So dn is the number of particles in du speed range. Du is the speed range. So dn is equal to 4 pi n m upon 2 pi rt to the power 3 by 2 exponential minus mu square upon 2 rt u square du. So here u is the speed of gas particles, m is molar mass of gas particle, T is temperature of the gas. When we are writing this equation, we are writing in this, when a gas is present, suppose helium gas is present in this container at temperature T. So when we are discussing, temperature is constant and the gas is fixed, and same gas is there, helium gas is there, so its molar mass is fixed. So molar mass is constant, temperature is constant, right? So how this distribution, how this number of particles are in different speed range, we are trying to understand. This equation is to understand that. This equation can be written in a simplified way, where this is a function related to speed, right? Variation of speed or distribution of speed of particles. So this can be this whole thing except du is denoted by a function of u, right? So I can write this big equation as dn is equal to g of function u into du. Now if I am saying that fraction of particles dn, if I take n on the left hand side, I can write dn upon n. dn upon n is the fraction of the particle in the speed range u plus du. So dn upon n is the fraction of particle. dn is the number of particles and dn upon n is the fraction of particles in the speed range du. So if I'm defining y as dn upon n du and u as x, because molar mass and temperature is fixed, we are studying the gas at a fixed temperature and gas is fixed, so molar mass is fixed. So now the other things are constant, like in this equation 4 pi will be a constant, m upon 2 pi rt to the power 3 by 2 is a constant. In this exponential term, m upon 2 rt is a constant, so that constant is b and this constant is a. So if I put this value in this equation, this whole equation can be simplified in this way. In place of dn upon n du, I am putting y. And in place of u, I am writing x. So this will be x square. M upon 2 RT will be b. And this whole thing will be a. So this is the equation. This equation is drawn here. So on y-axis, it is fraction of particles in a particular speed range. So dn upon n du, and on x-axis, it is u. So you can see that there are two parts of this graph. One is y is equal to x square, which is parabola. This parabolic path will dominate in low speed range. So this is according to parabola. The axis of parabola is y-axis. And in high speed range, this exponential part is dominating. So this exponential part is dominating in high speed range. So this is the explanation of the graph which is given in NCERT. This graph is given, but this graph can be explained with the help of this equation. So now you should not confuse in many books, right? This graph is given. In many books, this is given. What is this function of u? That is equal to dn upon du. If dn upon du, so we will say that this is the number of particles in a speed range du versus u graph, right? So there are two types of graph mentioned in books, so you should not confuse by both. This is also, if you see the nature of this graph, this nature of the graph will be same only, right? So there is no problem in nature of the graph. We want to understand that what is the area represented by these two graphs. So if I'm talking about this, if I take a shaded area, if I'm discussing about this shaded area, since if the value of du is small, the difference between this height and this height is small, so I can assume that this is a rectangle. Area of rectangle is length into width. So length is this height dn upon n du, and width is du. Du will cancel out. So this is dn upon n, means fraction of particles in this speed range. This whole graph can be divided in these type of ranges. So area of this graph is equal to, I can say, summation dni upon n. So if I take all these ranges, then dni, summation dni is equal to n. So that is equal to 1. So that's why I'm writing that if this is dn upon n du versus u graph, area of complete graph is equal to 1. And area of shaded graph is equal to representing fraction of particles in that speed range. If it is dn upon du versus u graph, then you can find out that if you take a small strip, the area of that strip is equal to y into x. Y is dn upon du into du. Du will cancel out. So this will tell the number of particles in this speed range. This is not fraction, it is number of particles in that speed range, right? So if I take this graph in a small strips, and if I find summation of that all, so I can say that summation dni is equal to number of particles in the container. So somewhere when they are mentioning that, when the examiner is asking, be careful about this. If it is number of particles in a particular speed range, then the area of this graph is representing the number of particles. If fraction of particles in a particular speed range, then the area, total area under the curve is equal to 1. So I think that there should not be any confusion, right? So from this graph, we are not going that how we have derived. When we'll discuss about JEE Advanced, we'll go through the derivation. But here, with the help of those graphs, this is the most probable speed. What is the meaning of most probable speed? Means there are different type of ranges of speed. This is a speed possessed by most of the gas particle. This is the maxima. So maximum fraction of gas particles possess this speed. So that speed is most probable speed. So this is maxima. For maxima, what we'll do, we'll differentiate with respect to x. So d, this is y. dy by dx is equal to 0. From there, we derive that most probable speed is equal to under root 2 RT by m. And same way from this graph, we can find out average speed. You should also know sometimes they will ask question about that. Average means what? Means u1. Basically, it should be dn1, u1, dn2, but I am writing in short u1 plus u2. If n particles are there, un divided by number of particles. So sometimes in question, they will give this value, or they will give these values and number of particles, and they will ask. But logically, they should give a large number of particles, then only valid. They want to just know that what is the meaning of average speed. Same way, URMS, when we are discussing about URMS speed, mathematically, if we want to write, this is equal to u1 square dot un square divided by number of particles. So again, when we are writing this formula, u average is under root 8 upon pi RT by m, or URMS is equal to under root 3 RT by m. These all formula is derived from this graph or this Maxwell equation. So now we know that what is the ratio of different type of speed. So UMPS, U average, and URMS. So if you simplify, you don't have time to solve an exam. If the options are only have fixed ratio, then there is no problem. You can find out that URMS is large. But it's better to you go and revise before exam, so that if they have changed the options in different values are there, then you will get confused that which value will be there. So 1 is to 1.128 is to 1.224. JEE मेंस में ये क्वेश्चन पूछा जा चुका है, वहां पे ऑर्डर बस एक ही था. तो already you know that this is the highest, and after that this will come, and lowest value is UMPS. There you will solve. But again, I will suggest that before exam you should read, and if you remember the value, it is better, right? 1 is to 1.128 is to 1.224, because if you try to solve in exam, it is not possible. Now the important point, For the same gas on increasing temperature, the graph becomes wide, and on decreasing temperature, it becomes narrow. What does it mean? That this graph is there, dn and du versus u graph is there at two different temperature, and they are asking about these two temperatures. So if the temperature is low, the distribution of speed will be small. Most of the gas particle is near about UMPS only. And when we are talking about speed, if speed is equal to under root, most probable speed is under root RT by M, right? So speed is on x-axis, right? And this height, if you see this height, dn upon ndu, if you simplify, the speed is directly proportional to T by M. But this fraction dn upon ndu, this is directly proportional to under root M by T. So this height is going to decrease. This height is going to decrease on increasing temperature. This height will be more when temperature will be less. That's why we are saying that at low temperature, this will be narrow. Means this height will be more and this graph will be narrow, and at low temperature, this will be narrow because this height will be more. And at high temperature, this height will be less because it is inversely proportional. So it is wide at a high temperature and narrow at low temperature. At large temperature, there are distribution of speed in different ranges, more particles in different ranges, right? Not most of the particle in a particular range of UMPS. At low temperature, most of the particle will exist nearby the UMPS only. So the graph is narrow. So this is about distribution of speed of particles at different temperature. When temperature is same and we are comparing two gases, we can say that at the same temperature, the graph is narrow for heavier gas and it is wide for lighter gas. For lighter gas, it will be wide because again, this is important. This height is directly proportional to under root M by T. So you already know speed is directly proportional to under root T by M. The height will be reverse of that. It is directly proportional to under root M by T. So from there, we can say that for heavier gas, if you forget about this and these graphs are there, you with the help of speed also, you can find out which gas is heavier and which gas is lighter. You know that this speed is more, right? And temperature is same. So you can write that speed is equal to under root 2 RT by M. So if this speed is more, definitely this mass will be less. So this is for lighter gas and this is for heavier gas. So we can say that if you forget about this, you can apply the concept of speed and find out that here, like if I'm saying gas is same and temperature is different, again you can find out this speed is more. So this more speed should be at, if molar mass is same, at high temperature. So if you don't know about this also, with the help of speed, you can find out that when the graph will be narrow and when the graph will be wide. So this is about the distribution. There are many things about this, but we cannot discuss here in mains. For advanced, we are going to discuss about it. So I have tried to cover almost all points in ideal gas equation. Hope it is useful to you. If you are finding these videos useful, share between your friends so that we get maximum benefit from it. Thank you.